Welcome everybody. It's the Sunday afternoon. Thank you for coming. So it's a pleasure to have Gautam Menon today, who will give the first talk in today's set of two talks. He'll be speaking on mathematical models for infectious diseases, and I'll allow Gautam to speak. Thank you.
Let me thank Dootika, Anita, Purvi, and Siva for this invitation. So I want to talk to you today about how one thinks about modeling disease spread. I want to give you the background to the field, give you a couple of terms that are used, and emphasize and describe why those terms are important. So let's just get straight into it with an example. So the example is a screen capture from a CNN program. I think it's their webpage, where it says 2 MERS patients die in South Korea. And this is dated June 2nd, 2015. The word MERS stands for Middle Eastern Respiratory Syndrome. So that's a short form for MERS. So now the question is, why was CNN putting some information like this on a web page on its own, sort of, it's an international news agency? Why did it consider this important enough to highlight? So this is the person who died, the sequence of people who died leading to that particular news item was a 68-year-old Korean man who traveled widely in the Middle East. So this picture here shows you where he traveled. He started off in Bahrain, went to the UAE, came back, went to Saudi Arabia, came back, went to Qatar, and then from there flew to South Korea. He reached South Korea on the 4th of May, and then he fell ill by the 11th of May, 2015. We actually know a lot more. This is the sort of picture of people who he infected. So he is that central person in red. And you can see various types of different colors representing his wife, visitors, healthcare workers, fellow patients, secondary cases. In fact, in some cases, there were people who visited somebody else in the ward in which he was placed and then caught the infection from him and then went off and infected somewhere else. For example, the patient's wife who's shown there. There's another patient in the visitor who visited someone else, who then later went and infected someone in China. Okay. So now the question is, how is it that we know so much about this particular patient, and why was so much trouble taken to track down the patient's contacts, as you can see in that picture? And that's the other way of asking, why are diseases like MERS special in any way, that we should take so much of effort to find out all of the contacts of the patient, as well as have CNN highlight it as a news item? The reason is that MERS is an untreatable disease. There is no vaccine for it. There is no medicine for it. It's also a disease that is often fatal. Patients die of it in a matter of days. It's an infectious disease, which you know because this person infected other people. It's an infectious disease with the potential of spreading across the world. It already moved from wherever he contracted it in the Middle East to Seoul, where it moved to infect other people. So therefore, it has the potential of spreading across the world. It's called potentially a pandemic disease. So MERS has been known for the last decade or so in Saudi Arabia, and luckily so far it's been confined to Saudi Arabia. So these little peaks here are the peaks that are recorded in each successive week. So you have 2013, 14, 15, 16, etc. The little red peak that you can see is a cluster around the cases in Seoul in South Korea. Okay. So it's really Saudi Arabia and a couple of occasional cases in the countries that surround Saudi Arabia. But the Seoul example was the one case where you had someone moving from Saudi Arabia to a distant location and spreading it there. This is of concern to people who think about public health, because Saudi Arabia hosts what is among the largest annual gatherings of people, somewhere between 2 and 3 million or maybe more, which is a Hajj. And pilgrims to the Hajj return to their countries, and currently somewhere around 190 countries contribute pilgrims to the Hajj. And it's very important to ensure that, like this gentleman who moved back to Seoul from Saudi Arabia, from visiting Saudi Arabia, that they don't carry back MERS with them, because then you have the potential of the disease spreading across the world in other locations, because it has been seeded by someone who came from an area where they were infected by it. This is not just a problem with Saudi Arabia and the Hajj, as I said, in terms of disease. Any gathering, and here is our own homegrown gathering, this is the Kumbh Mela, any gathering where there are a large number of people, where potentially disease can spread from person to person, should be a similar worry. So wherever you have a disease that spreads through person-to-person contact, the possibility that you will have a large outbreak of infection when many, many people gather together is a possibility that must always be mindful of. There are some historical precedents so right now we are living through probably the defining public health event of our century, which is the COVID-19 pandemic. But it's useful to remember that little more than 100 years ago, there was a similar pandemic with possibly even a larger footprint in terms of deaths and cases than COVID-19. And that was the influenza pandemic of Spanish flu between 1918 and 1919, roughly 2 years. Okay. This was important because it infected around 500 million people across the world, roughly about 25% of the world population. And numbers for those who died are not very easy to obtain, but you can say that roughly between 30 and 50 million people must have died of the Spanish flu. Records were not kept as well then as they are now, and even now they're not kept very well for deaths. In India alone, between 15 to 20 million people died, and this is about 5 to 10% of our population at that time. So roughly 1 in 10 people, between 1 in 10 or 1 in 20 people died as a consequence of Spanish flu. Mahatma Gandhi's grandchild died at that point. There were stories. The Hindi poet Suryakant Tripathi, or Nirala as he's known, has this harrowing account of seeing bodies float down the Ganges and also running out of firewood because there was just not enough firewood to cremate the bodies of people who died of the Spanish flu. So let's get to infectious diseases. And I would imagine that you know some of this, but just to remind those of you who don't remember this, infectious diseases are caused by some microorganism, a bacterium or a virus or a parasite, or sometimes even a fungus. These move between human beings either directly or indirectly. So direct contact is, for example, the handshake that you can see in the picture on the top right. There's an indirect contact way of transferring the disease from a person to person. If someone who has the disease comes and, for example, opens a doorknob or rings a bell, and somebody later comes by and touches that doorknob onto which these little germs, these microorganisms, these viruses or bacteria have been transferred, they can take that, wipe it across their nose or face, and then the disease is transferred from the original person to the next person. Droplets, this is important in the example of COVID-19. COVID-19 is a respiratory disease. It's transmitted through a respiratory route. And what happens is that when you cough or you speak loudly or you shout or you sing, you release large numbers, even within regular conversation or even breathing, you release numbers of droplets when you do that. And these droplets can carry little virus with them, small amounts of virus with them. And that virus can be ingested by someone who comes either at that time, directly standing in front of you, or even later because these droplets can be suspended in air for several hours. Okay? Which is why mask wearing is very important when we deal with COVID-19. Why aren't we always falling ill? For example, as I said, anyone who breathes, who's infected in the neighborhood should have COVID-19, is breathing potentially droplets of containing the SARS-CoV-2 virus, which causes COVID-19. The reason is that our immune system protects us. It's a very, very finely honed system inside our bodies that guards against anything foreign, any external. It can tell self from non-self. And the moment it senses an attack by a new bacterium, a virus, etc., it mounts a defense against that. So any sort of prior contact with a pathogen, bacterium or a virus capable of causing disease, can be sensed by the immune system, which will then react to it. This is essentially what vaccinations do. Vaccinations prepare your immune system to do exactly this. So let's turn to the question that I want to talk about today, which is how is knowledge about diseases and disease spread turned into mathematical models that help us predict their behavior, help us predict what might be going on or what might happen in the future. The whole question of how diseases affect populations is the field of epidemiology. Demos is people, epi is on. So what is on populations, what affects populations? And typically the question is you have some population of which a good fraction is in good health and some fraction is in ill health. And that ill health may arise as a consequence of an infectious disease. This proportion of good health versus ill health changes with time. So you can have a curve that looks like the curve that you can see on the right-hand side. And the challenge is to try and understand that curve, predict what might happen to that curve at some later point. And what sort of interventions might reduce the numbers of those who are ill and increase the numbers of those who don't have the disease. So here's a little bit of history. There's a long and fascinating history about infectious diseases that you would do well to go and read up sometime. But here's one example of one particularly important study, and that's a study due to John Snow in 1854, who studied cholera in London. John Snow came from humble backgrounds. He was the son of a coal yard laborer who became a doctor. And he was in London practicing at the time of the cholera epidemic between 1948 and 1959. So it was he who proved that water pumps were a source of cholera. And he did this in this extremely interesting way that I will just show you now. So here is a part of London near a region called Broad Street. The dots there are dots of cases of cholera. Okay. What's also marked here in the crosses are the locations of the pumps across this region. So what John Snow did was that he did, this is, you could call it spatial epidemiology, which is really amounts to taking a map and mapping out the locations of cases, the houses of the cases. And he noticed that there was a cluster of cases really around the pump labeled A on Broad Street, as opposed to pump C or pump D or pump B, etc. So then he said, maybe there is something in the water that is infecting people, and we just closed that pump and provided an alternative source of water, then the number of cases would go down, and that indeed is precisely what happened. The Broad Street pump was the primary source of cholera infection. He also noticed, if you will notice on that picture, there are two blocks that have no cases at all. And those were the blocks that had their own source of water. They were supplied by a distillery, the Guinness distillery, so they did not need to use the water that came from the pump. So the pump was closed and removed, the outbreak ended. And remember, even at this time, there was no clear knowledge of bacteria or viruses or the fact that they could actually cause disease. But nevertheless, the study was able to identify water as a vehicle for transmission of the disease. So here's a little bit more history, and that's about models of disease. And the most famous mathematical model of disease was first developed by two scientists, and one of these scientists had Indian connection. For many years, the contributions of this model were not recognized, and it was only much later, maybe about 30 or 40 years later, that it came back into prominence. And right now, it underlies the way that we think about infection, the language with which we think about infectious diseases. And this model is called the SIR model for reasons that I will explain to you just now. So this model is due to two people. One was Mr. McKendrick and one was Mr. Kermack. McKendrick was born in Scotland. He trained as a doctor, and then he joined the Indian Medical Service. And he became the director of the Pasteur Institute in Kosoli. So that's his Indian connection. He went back to England in 1920 and then went back as superintendent of the Royal College of Physicians in Edinburgh. He was superintendent from 1920 to 1941. Kermack, on the other hand, interestingly trained as a mathematician, but then worked as a chemist for many years at the same Royal College of Physicians laboratory. Unfortunately, even while he was quite young, he had a laboratory accident that blinded him completely. So he was a practicing chemist at his table, but once you are blinded, you cannot do the same bench work that you did anymore. And therefore, he returned to thinking about mathematics, and he continued his research in collaboration with McKendrick. So Kermack and McKendrick worked together to develop what is now called the SIR model. They tried it out on data that Kermack had, that McKendrick had from his studies in India, the plague epidemic in Bombay in the early 1900s, around 1905, 1906. And then they found an extremely good fit to the data that they were able to derive using the mathematical model. So let me explain to you what that model is and what it does. So first of all, we want to discuss disease in some population of individuals. These individuals are heterogeneous. They're not the same. You are not the same as me, you're not the same as Siva. We all have different susceptibilities to disease. We have different immune systems. We have different responses. We have different pre-existing conditions. Nevertheless, we can sort of imagine that we're thinking about a disease in which everyone is susceptible to the disease, could potentially catch that disease. Once someone is infected with that disease, they become infected. That's a different category altogether. And infected people finally will either recover or die, and that's a separate category. Let's assume that they won't die at the moment. They just recover from the disease. So it might be as mild, for example, as the flu. So we're going to ignore the heterogeneities between people. We're going to go back and put this back later when we talk about different types of models. But for the time being, we're going to ignore it and just categorize everybody either as susceptible, infected/infectious, that's what it's meant, as well as recovered. So that's how we're going to simplify this. And that's where the S and I and the R come together in the SIR model. So if you're susceptible, you've not been exposed to the disease, you're not infected by the disease, but you could potentially become infected. If you're infectious, you can transmit the infection from yourself to someone who is susceptible. If you have recovered from the infection, therefore you cannot fall ill again. You're not susceptible again. You're now permanently recovered from that particular disease. The next step is to think of all of these groups, the susceptible, the infected, and the recovered groups of people, as belonging to separate compartments. The word compartment is used here, that's a technical term. So these models are also called compartmental models. So you have a bunch of people in the S compartment, the susceptible compartment. You have a bunch of people in the I compartment, the infected compartment, and you have a bunch of people in the R compartment, which is the recovered compartment. And you label these compartments accordingly. What you're interested in modeling or figuring out is the number in each of these compartments. For example, are there 1 million people who are susceptible, 100,000 who are infected, and 50 people who have recovered at some point during the disease? And you might want to ask how these numbers change as you go forward in time. The next assumption that is made, this is often a somewhat unrealistic assumption, is that all members of the population interact with each other. So any individual can contact any other individual. This is called the well-mixed approximation, or in other fields, the mean field approximation, but it usually is used to make a calculation tractable. So here is putting the three compartments together, the S compartment, the I compartment, and the R compartment. And you go from being susceptible to being infected to being recovered. So that's where the dark arrows actually point towards. Okay, so that's a transition between compartments. But there's also an influence between compartments, because the susceptible people can't go to the infected compartment without something special happening to them. They must be infected. In order for them to be infected, they must come into contact with someone who is already infected. So there must be some influence that takes the infected compartment and connects it in some way to the susceptible compartment. And that's the dotted line that you can see, the dotted arrow that you can see connecting the I and the S. So there are transitions between people moving in numbers changing between the S and the I and the R, but there's also influences. The number of people in the I compartment influence the possibility that someone in the S compartment can develop the infection. So here is sort of working it out. If S is the number of susceptibles, I the number of infected, and R the number of recovered, the rate at which S changes is proportional to the number of contacts between S and the I, of course, because only some fraction of those contacts will actually lead to a disease. So that's where the proportionality constant comes in. The S comes in because, of course, the number of people who are susceptible who change is proportional to the number of people who are in the susceptible compartment to begin with. You multiply that by the fraction of the infectious population, that if you contacted people at random, what fraction of them would turn out to be infected, and therefore to change you, to take you from the susceptible compartment to the infected compartment. So because the number of susceptibles must always decrease as a consequence of infection, there is a minus sign that is over there. There is a constant that tells you what is the infectiveness of the infectious people who you come into contact with. That's a constant called beta. And then the S, I, and N are all terms that we just justified now. The fraction of the infectious population is I over N. S is the number of susceptible people. So here's an equation that actually says ds by dt is minus beta times S times I divided by N, where N is the total number of people inside the population. Okay. The beta here, if you look at the dimensions of the quantities on the left and the right-hand side, the S and the I and the N are purely dimensionless quantities. They carry no dimension. They're just a number of people, 20, 46, 55, etc. But ds by dt has the dimensions of 1 over time, because the t is measured in units of time. Therefore, the beta has a dimension of 1 over time. And therefore, beta is an inverse time scale reflecting the rate of infection. Okay. The next part to it is, of course, the second arrow. That is, how do people go from being infected to being recovered? And that's simple. After a certain amount of time on average, you go from being infected to being recovered. You recover naturally across some time scale. There is a rate associated with that. And that equation is just dr by dt is proportional to I in some ways. It is just gamma times I. So the increase in the numbers of people who are recovered reflects the number of people who are currently in the infected compartment and about to leave it. Okay, so those infected recover at some rate. The number recovering is proportional to the number that are infected. So that's the equations on the left-hand side. The first equation is ds by dt is minus beta times S times I divided by N. That's the equation that we just worked out. So those are the number of people leaving the susceptible compartment in order to become infected. The same number of people must be accepted into the infected compartment. Therefore, whatever term that you have on the top equation, the minus beta Si by n, must appear in the middle equation for how I changes, but with the opposite sign, because those that the S compartment loses are completely gained by the I compartment. So that's the di by dt is beta times Si divided by n. But of course, there's also a loss from the I compartment because people recover and they leave the I compartment. So that is the minus gamma times I. Again, the sign is important. Minus says the I must decrease. And all of those who leave the infected compartment must go to the recovered compartment. So the minus gamma I must be compensated by plus gamma I on the recovered side. So dr by dt is plus gamma I. And all of these three equations together are now coupled equations for S, I, and R. Okay. Notice that if I take the left-hand side of these equations and add it up, I get d by dt S plus I plus R is minus beta minus gamma plus gamma. All the terms on the right-hand side, when added together, will vanish. Therefore, d of S plus I plus R must, of course, equal 0. And that's, of course, obvious because this is just the total number of people in the population. We assume that there are no births and deaths, and therefore the total number across each compartment remains constant. All that can change is the allocation of people across these different compartments. So that's your equation to the left. I'm going to make one minor change to this equation, just a terminology change. Instead of capital S, capital I, capital R being the total number of susceptibles infected and recovered, I'm going to divide each of those by n and just relabel that as S again. So if you just work that out carefully, you will see that the factors of n have vanished, but the equations, the larger set of equations on the right-hand side, are now for the fraction of the population that is susceptible, the fraction of the population that is infected, and the fraction of the population that is recovered. Each of these fractions can go between 0 and 1 because they're a fraction, they cannot exceed 1. And the sum of these must always add up to 1 as a requirement because the total number of susceptible, the total number of infected, and the total number of recovered is capital N. And as the fraction of the total population, which itself is capital N, this number must add up to 1. This ratio must add up to 1. So these are the famous SIR equations of the SIR model that were originally written down by Kermack and McKenna. So now that we have these equations, these are nonlinear first order in time differential equations. They're nonlinear because of S and I appearing together on the right-hand side. So these equations have no analytic solutions, but nevertheless they have an easy numerical solution. The number of susceptible. So the way you do it is that you start off with almost everyone susceptible. Let's say 99% of people susceptible, but you introduce one infected person, 1% of infected people into the population. You need to do that because if there were no infected people in the population, no one would get infected because you need an interaction between susceptible people and infected people for susceptible people to get infected. So the numbers of susceptible people come down. That's a blue line that you can see. Initially, it was close to 100%, and then it began to come down once more and more people left the compartment because they became infected. The number of recovered people goes up and saturates, and finally, it sort of goes to a large value that you can see. That's the green line there. The red line that you can see that goes up and comes down is a line that corresponds to the number of infected. In the beginning, it's only that small 1% of people infected who was actually there. That number grows as people leave the susceptible compartment, they get infected and they move to the infected compartment. So you see the peak that comes there. And then after that, you see the decline as people recover and they move from the infected compartment to the recovered compartment. Okay. So there are your equations that I wrote. The solutions of these equations are mirrored in the solution on the left-hand side in those graphs that I showed you. This has a standard peak and decline of infection that we've come to know from COVID-19. And all I will point out here is that these equations have, there are two terms that appear in these equations. One is beta, one is gamma. There are two constants that appear here. And the only sensible dimensionless combination of these, both are rates, is beta divided by gamma. So beta divided by gamma is a dimensionless constant. It's so important that it has a name. It's called the basic reproductive ratio. And the basic reproductive ratio really controls all of the behavior of this set of equations. So let's see what we can do. Let's imagine taking gamma equal to 1, just to standardize everything, and varying beta. So those are the pictures that you see on the right-hand side, first for large beta, and then as you decrease beta. And you can see that the effect of decreasing beta, or effectively of reducing what I call the basic reproductive ratio, is that the peak of the curve comes down and then it shifts to the right. Okay. So for the largest values of beta, you have a sharp curve that rises very fast and then comes down. And that rise happens fairly early on. The smaller that beta is, the more gentle that rise, the lower the peak, and the longer it lasts onto the right-hand side. Okay. And of course, from here, you can also find out the number of recovered, the number of infected. All of this is there in the set of equations for you to look at. What I want you to notice is that we've shown you beta all the way up, right from 9, 8, 7, 6, 5, etc., to a number that is smaller than 1. The moment beta drops below 1, the number of infections that you start out with decreases monotonically to 0. In all other cases for beta greater than 1 or the reproductive ratio greater than 1, you had first a peak and then a come down. And that peak, of course, went down as you made beta smaller and smaller, but there is a threshold value of beta beyond which you don't see a peak anymore, you just see a decline all the way. So below this threshold value of beta, in this particular case 1, you have a disease which tends to die out. Above it, it tends to grow. So here's the logic behind this. So let's look at these equations again, and let's look at the equation for the infected numbers. So the infected numbers is di by dt is beta times s minus gamma times I. What we're going to assume is that s is very close to 1. That is, the population is very largely susceptible. And then we're going to add a small number of infectious persons. Okay? So then the equation that you get is basically s approximately equal to 1, set s equal to 1, di by dt, the change in the numbers of infected as a function of time, is beta minus gamma times I. And now you can see what the significance of beta and gamma separately are. If beta minus gamma is positive, di by dt will increase in time. If beta minus gamma is negative, it will tend to decrease in time. So as a function of, so that's really the question of, is beta divided by gamma less than 1 or greater than 1? Okay. If beta by gamma is greater than 1, infected numbers will grow. If beta by gamma is less than 1, infected numbers will go down. This, as I said, this particular quantity, the ratio beta over gamma, has its own name. It's a basic reproductive ratio. Here's another interpretation of what it actually is. So go back to that same equation that I wrote down. Di by dt is beta minus gamma times I. Let me incorporate gamma, the rate, into the definition of the time. So di by d gamma t together is beta by gamma minus 1, which is r naught minus 1 times I. Call gamma times t as gamma tilde. That's my new time variable, my new scaled time variable. So di by d tilde is r naught minus 1 times I. I'm now going to set the number of people I equal to 1. There's one, let's say, person in the population there. D tilde equal to 1. So what happens is I at time t plus 1 minus 1, the increment or the change in the numbers of infected from the initial person who was infected is just r naught minus 1. Okay. So I at t plus 1 is r naught. So that is the interpretation that if I start with one person initially who is infected, r naught is the number of people who are infected after an amount of time has passed, which is really the time it takes for the person to recover. We'll come back to this intuition that this result provides a little later, but let me just emphasize the importance of r naught. So the questions that you might want to ask is, will the disease spread? How many people will be infected? How many could die? And all of this depends upon just the basic reproductive ratio, r naught. So as we figured out then, r naught says for every one person who is infected, how many people will they subsequently infect, given that everybody else is now susceptible to the disease. For Ebola, that number is 2. For swine flu, that number is 2. For HIV, that number is 4. For measles, that number is 18. So measles, one person with measles in a room full of people who don't have measles could potentially infect a very large number of people right at that point. Okay. So if R is greater than 1, the disease explodes, numbers increase, because at each stage, you're infecting a larger number than were there at the previous stage. If R equal to 1, that's an interesting situation. For every person who recovers, they infect one person before they recover again. So the numbers of people in the population remain more or less constant. This is called an endemic disease. So malaria is endemic in many parts of South Asia and Africa. That's what it means. The numbers may fluctuate a little bit from time to time, but there's always a steady background of people with that infection. On the other hand, if R is less than 1, systematically you infect fewer people at the next time step. So the disease dies out rather than grows or remain constant. So if you plot the basic reproductive ratio here on the x-axis and the fraction of infected on the y-axis, the smaller the reproductive ratio, the smaller the fraction who will be totally infected. And below 1, of course, there is no epidemic at all. But then above 1, as you increase, you can go up, you can see as I increase the reproductive ratio, I have more and more people being infected. And by the time I get to above 5 or 6, in terms of the reproductive ratio, I've already infected close to 90% of my population at the end of the epidemic. You can look at these equations as dynamical systems with initial conditions S of 0, I0, R0, etc., and manipulate these equations in interesting forms. For example, look at di by ds, which is di by dt divided by ds by dt. And you can write it in the form minus 1 plus gamma over beta. Just go back to the equation that I had earlier. And then integrate this to give you the phase plane trajectories. And here you can see that I plus S minus 1 by R naught log of S is I naught plus S naught plus 1 minus 1 over R naught log of S naught. Everything on the right-hand side reflects your initial condition. Everything on the left-hand side is a constant along any trajectory that the disease might take in terms of I and S. Let's get to another explanation of one of these questions that I told you about earlier. Why should you vaccinate against a disease? You can see the equations are basically SIR model equations in the top right-hand corner. And now stare at that equation that I've shown you right at the top. For the number of I to decrease, for the disease not to propagate, beta S minus gamma must be less than 0, because then di by dt is minus sign something times an I. If this is true, then beta S must be less than gamma, again rearranging that term. And if I remember that beta over gamma is R naught, this says that the number of susceptible people must be smaller than 1 over R naught. The susceptible fraction must be smaller than 1 over R naught. How can I accomplish that? Let's imagine that there is some magical way in which I can paint people, when the analog is vaccination, so that those people who I mark will not fall ill to the disease. They don't contribute to the susceptible population. In that case, I'm replacing S by S into some 1 minus P. I'm reducing the fraction of S that is susceptible. And I can go back and ask, what is the condition? How does the condition S less than 1 over R naught map onto a relationship between R and P, the fraction of the population that I need to protect against the disease? Binary algebra, you can figure that there's a threshold PC, which is 1 minus 1 over R naught, such that if I vaccinate that fraction of the people, the 1 minus 1 over R naught fraction of the people, then effectively the reproductive ratio falls below 1, and then the disease will decline. So this is useful because it says that A, I don't need to vaccinate everybody in my population. I just need to vaccinate a critical number of people in the population. That number, that fraction is given by 1 minus R over R naught, 1 minus 1 over R naught. The larger the R naught, of course, the more people I have to vaccinate. Okay. So for measles, it's 1 minus 1 over 18, which is a number close to 98%, which is why it's important to vaccinate children right in the beginning against the measles. That's the standard immunization schedule that we have in India. This is called herd immunity. The fact that you don't need to vaccinate everybody or protect everybody, but only some fraction of that, which depends upon the properties of the disease, in order to protect the rest of the population. So vaccinating sufficient numbers in a population provides you herd immunity. That's the important point to make. How many people will be infected? The answer depends upon R naught, and we saw that when we plotted the curves for that. I didn't show you how that was obtained, but the larger the R naught, the more the number of people who are infected. And of course, now you know the answer of why we should vaccinate against a disease. You vaccinate susceptible people, remove them from the susceptible population, and reduce R naught. But you don't have to vaccinate in everybody because of herd immunity. And for Ebola, as I said, R naught equal to 2. It's enough with the Ebola vaccine to vaccinate 50% of the people to protect the rest of the people who are unvaccinated. This is an important point to make because not everyone can be vaccinated. There are people who, for example, have pre-existing conditions, a weak immune system that ensures that they will react badly to a vaccination. So you're not supposed to take a vaccination. So what we would like to do would be to protect them. One way of protecting them is to reach herd immunity in the broad population that can take a vaccine. How do you improve this model? I'll tell you a little bit about how to improve a simple SIR model. You can add more compartments to the model. You can structure the compartments in interesting ways. You can change the nature of contacts between these structured compartments. You can work with what are called metapopulations, and you can work with stochasticity. So all of these changes are changes made to the original SIR model or more complications of that. So one thing that you can do, and this is appropriate for COVID-19, is that for COVID-19, there is a not too short period in which you're exposed to the disease, the virus is building up in your body, you're potentially infectious to other people, but you're not symptomatic. You don't show symptoms yet. So one way of accounting for this is to add an additional exposed compartment. So you go from susceptible to exposed to infected and to recovered. The second thing that you can do is to recognize that disease doesn't impact everybody the same way. You may be less likely to be infected and show symptoms if you're a young person as opposed to you're an old person. Okay, so you can imagine each of these compartments being broken up into sub-compartments or age structure, such that the first little band represents 0 to 40, the second 41 to 60, 60 to 72, etc., etc. So you have structured your compartments by age, and you can now put in the risk of infection in different ways across these ages. You can put in more information. I said that you needed people in the S compartment to contact people in the I compartment inside the population. But now that you've broken it up into these age brackets, you can say, what do I know about how much someone who's 20 years old might contact someone who's 80 years old? Little children stay with their grandparents. By the time you're older, you don't see your grandparents so much anymore unless you happen to be living in the same house. So there's a lot of social information here about the contacts between different age groups that can be put into this calculation through what are called contact matrices. We just sort of imagine that everybody interacted with each other just here, but that's not a realistic situation. You can think of what are called meta populations, which are groups of populations, say one city here, city of Bangalore, city of Chennai, city of Delhi, city of Bombay, and you have people moving from these different populations across each other. So each of these populations has their own SIR model in which they have their own set of infection, but this ability to move from one box to the other can convey an infection from one point to another point. If there was nobody who was infected in this particular compartment, that can change because someone who's infected in some other location, from some other compartment, from some other population, can come and add an infected person to this population and start off the epidemic locally. These are also called patch models. Models for vector-borne diseases, for example, malaria, etc., must describe the life cycle of the mosquito. So it just gets more complicated in terms of the different types of compartments that you have to write down. If you have sexually transmitted diseases, for example, you can have a high risk and a low risk population. And it's important to model that particular structure when we talk about such diseases. The next thing that we haven't spoken about, remember that all the models we spoke about, the SIR model is a deterministic model. With a certain initial condition, it will always give you the same answer. It gives you a peak in the infected, and then that peak declines. A stochastic model is a model that puts in intrinsic noise and stochasticity into the description of how cases might grow or shrink. So the smooth picture that you saw on the left-hand side is typically replaced in real data by this jagged picture that you see on the right-hand side. That's for daily confirmed COVID-19 cases in India across a certain period of time. And see that it fluctuates. It sometimes goes up, goes down, goes up. It's very jagged. Even though you can sense the same broad trend that you saw in the picture on the left-hand side, there's much more structure and stochasticity in the picture on the right-hand side. The stochasticity comes from multiple reasons. Not every exposure leads to an infection. Not all infection leads to a disease in terms of symptoms. And of course, inadequate testing, reporting delays, suppressed data, inaccurate data, the spatial heterogeneities between, for example, a city, a rural area, and an urban area could also be important in making sure that the plot of cases is not a smoothly rising plot, but shows these ups and downs. The last thing that I want to finish up is two conceptual ways of thinking about diseases that are somewhat different from the earlier picture that I showed you. One is an idea based on networks, and the second is what is called individual-based or agent-based models. When we think about networks, we understand that we interact always with some subset of people. Okay, we don't, the motivating assumption in writing down the SIR model was everybody interacted with everybody else. But that's not true. Your grandparents interact with a smaller group of people than you do, or a child does, or a professor does. Professor who sits and gives multiple lectures in classes across the week has a large number of people that they interact with. A vendor, someone in a vegetable shop, has a large number of people, customers who come to them to interact with them. So it's these links between people, in particular physical links where you have two people coming close to each other, potentially where one being infected, one being susceptible, and able to transmit the disease from one to the other. This is what motivates the idea of the networks of interaction between groups of people being significant in understanding how disease must spread. So these networks can be many types of networks: emotional, transactional, contact networks, social networks, etc. All of these are broadly subsumed into ideas regarding networks and their application to disease spread. People, in fact, work on this. This is an example of how you track swine flu transmission. They looked at how it spread within a school, where they actually looked at who was sitting next to who in school, how it actually moved from person to person, how it moved outside schools. When children left school and then went back to their families, how did it circulate within their families? And this sort of chart tells you how the nature of the interaction between people, the people they did not even infect, which are these dots, these little circles that you can see there, plus the people who they actually managed to infect, divided between male and female. And results like this, or studies like this, are very important, because in this particular example, this shows that the outbreak did not slow down the rate of transmission, since this really happened through a network of friends, and friends, whether they met in school or outside school, remained friends. And that's where the transmission actually happened. So closing down a school didn't make too much of a difference to stopping the spread of the disease. Agent-based models are, in a sense, also like network models, but they incorporate some idea of geography and location inside them. So for example, you model in each individual. So these are all individual models, individual-based models, both the network model as well as the agent-based models. There are large numbers of such models at the moment, where you simulate the behavior of each person, who they interact with, where they travel to, how they come back, their own individual susceptibilities, etc. Usually, in order to do this, you need a synthetic population, a computer-generated population that is as true statistically to the real population as you can possibly make it. And then, as I said, you put it on a geographic background, you look at people interact, and you can study geographical variations in how the disease is actually spread. And you can incorporate a lot of complexity into how you describe the agent. Let me finish up with just one important point, and this is very crucial. We define R naught to be beta divided by gamma, but another way of thinking about R naught is that it has three parts. The first part is transmissibility, the probability of an infection given a contact between a susceptible person and an infectious person. So that's the tau that you can see over there. The second is how many contacts do you have in the first place on average. So the C bar is the average rate of contact between susceptible and infectious people. The D there is the duration of infectious, is how long do you stay infected. So D is really the 1 over gamma that appears in the expression for R naught over there. And beta contains within it both the efficiency with which you transfer the disease from a person to a person, as well as the number of contacts. If you have a large number of contacts, but you have a small efficiency of transferring disease, you can still wind up with the same number as you would get a number of new infections that you might generate, as if you had a small number of contacts, but were much more efficient at transferring the disease. This also suggests how you might control epidemics. That's because you can work on each of these quantities independently. You can reduce transmissibility by developing vaccines and by using antiretrovirals to reduce the amount of viral load inside your body. And this is a strategy for AIDS. You can decrease the mean contact through isolations, quarantines, health education programs, lockdowns, etc. Just reduce the number of people contacting each other in a given unit of time. Reducing the length of the infectious period, therapeutics, antibiotics, boosting immunity, etc., will all help you recover faster. Indeed, also vaccines also help you recover faster, even if you happen to be infected mildly with the disease after you're vaccinated. All of public health that relates to thinking about infectious diseases from a mathematical point of view, from a practical point of view, really looks at these three major avenues in which to reduce the probability that someone will infect someone else. So let me finish up here. I gave you some background, a bit of history about pandemics. I told you about compartmental models, the canonical compartmental model, the SIR model, or the Kermack-McKendrick model. We discovered the importance of the reproductive ratio. We talked about herd immunity. We talked about structured populations, age-structured populations, contact-structured populations, meta-populations. We talked about the logic of public health measures. We did that just now, of how you could control each of the three terms that enter the definition of a reproductive ratio. We talked about different models. Adding complexity was where we talked about the agent-based, the age-based stratification, etc. Then we talked about network models and agent-based models. There's two examples of how primarily computational models can be used to move beyond the limitations of simple mathematical model that you have to solve either on a computer or with pen and paper, to be able to incorporate much more detail into your description of the basic units that enter the disease. So let me stop there and thank you for your attention, and I'm happy to take questions.
Thank you very much, Gautam. And if you want to ask questions, you can unmute yourself and ask.
There's no such thing as a silly question. They're all the same. So please ask whatever it is that you would like to ask.
We'll just give it a minute. It take time to warm up a little. Just wanted to check. Naveen, they can unmute themselves, right?
Yes, sir.
Yeah, thank you.
Good afternoon, sir.
Hi.
And this side. Sir, I just want to know that from this system of equations, how can we get to know that how long a disease or pandemic will last?
So for that, you have to solve those set of equations. Once every disease carries with it a value of R naught. So once I tell you that COVID-19 has an R naught of somewhere between 2 and 3, and that R naught can change, of course, if you put in various types of interventions like lockdowns, etc. So one thing is to be able to match the data that you see in terms of what the model predicts. But that model will predict that the number of infections will rise and then it will come down as you put in various types of interventions, etc. And how long it lasts, for example, at the peak might happen 6 weeks from now, 4 weeks from now. And then you can say maybe roughly that much of time it will take to go ahead before it actually goes away. And
Okay,
this
thank
is
you, sir.
complicated because there are many ways in which you can intervene. So it's not very simple. The simple equation that I said had just one value of the reproductive ratio that didn't change in time. But unfortunately, that's not real life because everything that we do to intervene will change the R0. So that becomes a much more complicated calculation to implement. But thanks.
Yes, sir. Yeah, thank you, sir.